This video is about torque. We're going to look at torque, but we're not going to introduce angles quite yet into torque. Alright, so torque. There are two ways to look at torque. You can look at torque radially, with using radians and things like that, or you can look at it linearly. So, torque is the effectiveness with which a force can cause an extended object to rotate. Okay, so if I apply the same amount of force at two different points on a door, the farther I am from the hinges, the more effective that force is. Okay, because at one point the door may not move, at the next point it will. Okay, this is also known as angular force. So torque is angular force. Now the torque equation, using our fun new letters, is right there. I equal I times alpha, or moment of inertia times angular acceleration. Now in equilibrium, you're not going to be accelerating angularly. You're not going to be making more revolutions per second, so that would be 0. So your torque would be 0 as well. Now if we're going to switch over and look at it linearly, and we're going to spend some time with this first. Alright, torque is R cross F, which is basically RF sine theta. So the top one is in your reference table, the bottom one is not. Okay, so you just need to realize that cross means sine theta. Alright, the units for torque is newtons times meters, and R is the distance from the axis of rotation. Okay, F is of course force in newtons. So if I was going to look at R, if I look at the pictures down at the bottom, this is my axis of rotation. The R for that mass would have been right there, while the R for this mass is right there. Okay. Now there's that sine theta. We're going to not really spend time on that. That angle is the angle between R and F, but we're going to ignore it for this lesson. Okay, we'll come back to it later. So right now, you can think about your torque equation as being just RF, because sine theta will be 1. Alright, now, positive and negative. Clockwise is negative, counterclockwise is positive. There are two ways that you can remember that. One, if you use your right hand and you curl your fingers in the direction of the rotation, if it makes a thumbs up, it's positive. If it makes a thumb down, it's negative. Okay, just remember to use your right hand, otherwise you'll be screwed up. And I like number 2 better, personally. Clockwise is negative because there's one C, and C is negative. So counterclockwise, 2 C's is negative times negative, which equals positive. Alright, so when you're solving torque problems, there are 4 steps that you probably want to go through. Step 1, identify your axis of rotation. Where is that pivot point? In that case, it's right there. Okay, let me do that in blue. Number 2, you want to identify all forces acting on it. Okay, this is when you're doing it with a linear torque equals RF. So if you look at the forces acting on it, you're like, okay, well here's one, and here's one. So I have my axis of rotation and my forces acting on it. Please note, if the pivot point's not at the center of mass, that's important. Okay, so not at the center of mass, and if the mass isn't negligible. So if I look at this beam right here, okay, with no other forces acting on it, it wouldn't balance. And the reason it wouldn't balance is because the center of mass of the beam is not at the pivot point. Okay, so that means I need to take that force into account. So you find the center of the beam, and you have the force of gravity of the beam at the center of mass. So you got to take that into account. And we'll see that a couple of times. All right, number 3, you want to sum up your torques. Okay, so you have all your forces, you have all your radiuses, you're going to sum up your torques. So in this case right here, sum of torque is equal to, now, counterclockwise is positive, so I'm going to start with the positive direction, which is that one. So I have, let me see, this one is a distance x. I'm going to make this distance, just so we can have numbers, I'm going to make that 10. And I'm going to make this 5. And that makes that 15, so I'm going to make that 2.5. Okay? So if I'm going to sum up my torques, I'm going to say, okay, force 1 is here. It's F times R, so it's the sum of F times R. So that would be 200 times 10 plus second force, which is the center of mass of the beam, which is 100 times its distance R, which is 2.5. And then the other one's going to be subtracted because it's in the opposite direction. And that would be 500 times 5. Now, if all that equaled 0, you would be in equilibrium and it would be balanced. It wouldn't be rotating. Okay? If it doesn't, then it's not. So if 200 plus 250 minus 500 does not equal 0, which it does not, then it will be rotating. You'd have a torque of 50 Newton meters. Now, step 4 is one that you don't always have to take. It's kind of one of those that if you're stuck, this is what you take. This is the step you take. It'll help you with that last step. Is sum up your forces. Okay? Going back to the previous units, sum of forces in the X and Y. Okay? In this case, I could do a sum of forces. I have 3 forces acting down. I have a 200 Newton force acting down. I have a 100 Newton force acting down. And I have a 500 Newton force acting down. Now, this isn't accelerating downwards, right? It's kind of sitting there, which means I also have a force acting up. So that, I'm going to call him my normal force. And if I wanted to, I could decide on the force acting on that. Right there. All right, here's a fun example. I have an 8-meter uniform plank of mass 100 kilograms. It's a rest on top of the building. 2 meters is extended over, and I've got this person, 75 kilograms, that's trying to walk off the edge. And he doesn't want to tip over and fall to his death. So we're going to see how far he can walk over. All right, our first step is identify the axis. That axis is right there. Next step, identify the forces and their R's. All right, so this guy has a force of gravity. Okay? And his R is unknown. Okay, that's what we're solving for. So that is 750 Fg equals mg R. Okay? The other force acting on this system is the center of mass of the plank. Now, if this is an 8-meter plank, 4 meters out, halfway down, is the force of gravity of the center of mass. And that R is going to be 2 because the center of mass is halfway down the plank, leaving you with a total of 6. So that is force of gravity of center of mass times R, which is 1,000 Fg equals mg times 2. Okay? And now, there could be another force acting on it. There could be a normal force pushing up. However, they're asking for the point right before it begins to tip, which means your normal force equals 0. Okay? Under normal circumstances, if he wasn't out there, there would be a normal force. Something would have to counteract gravity. All right, so there we go. That's 0, so that goes away. And we can start working. Now we need to sum up our torques. Sum of torque is equal to the sum of my FR, which in this case, counterclockwise is positive, so that would be 2,000 minus 750R. Now, just before it starts to spin, means the sum of my torque is 0. So, 2,000 is equal to 750R. Divide by 750, and you get your R. And your R should equal 2.67 meters. Now 2.67, that means he can walk 2 2/3 meters past the end. Now if there's only 2 meters here, he can walk all the way to the end without falling. He could actually walk to there without falling. So he's safe in this case. All right, a meter stick is supported on each side by a spring scale. All right, so let's draw a picture since there isn't one provided with us. We've got a meter stick. Each side has a spring scale, and there's a mass hanging from so that the left side is larger than the right. So we've got the force on the left, we've got the force on the right, and we've got the force of gravity of the mass. Now, the meter stick is negligible mass, which means it doesn't have a center of mass. We don't care about it. Okay, it does tell me that my FL is equal to 2FR. Okay, there's my pretty picture. Now let's start going through our steps. Now, our first step is identify the axis of rotation. Now, they didn't give one to you. It's not actually rotating, but that means that you get to pick your axis of rotation. I'm going to pick the location of the mass. You're going to always want to pick a location of one of the forces. I'm going to pick that one because we know, oh, that should be an FR. Sorry. We know that FL is 2FR, so if I knock that FG out, that means that I'm only going to be dealing with one variable, which will make life a little bit easier. So I'm going to pick that as my axis of rotation, so that my R of FG is 0, and that will go away. Identify all the forces. Well, I kind of already did that. We got FL, we got FR, we got FG. Now, each of their R's. This is a meter stick, right? So the total distance is 1 meter. All right, so if I'm going to say this side is R, that means that this side is 1 minus R. So I've got my radiuses. And this one is, of course, 0 because it's at your axis of rotation. Sum up my torques. Sum of torque is equal to, now counterclockwise, is FR, and that's going to be times R minus clockwise, which is FL, 1 minus R. And it's not rotating, so that's 0. Now, I could include this in there, but that's just going to be 0. So plus or minus 0. All right, let's simplify this down. FR times R minus, now my left force is equal to 2FR. So I can put that in. Okay, simplify down even more. FRR minus 2FR plus right force times radius equals 0. Okay, now we put these together, and I've got 3 right side force times radius minus 2 times right side force equals 0. Do the math, and I can actually make them equal to each other. FR will cancel out, and my radius is 0.67 or 2/3. So that side, I am 0.67 meters away. Now, if a mass is 10 kilograms, what's the force of gravity, what's the force reading on each one? So we know that the one is twice as big. We don't know the force in it. This is when we start looking at number 4, because we can't do it with the sum of torques. We've already done sum of torques. We did 1, 2, 3. We got everything we could from it. We didn't get enough. So now we have to look at the second one. This is when we start doing sum of forces. So if I was to do sum of forces acting on it, okay, I've already identified my forces, so I'm basically good to go. I have a rightward force acting up, I have a leftward force acting up, and I have the force of gravity of the mass acting down. Okay, now all that equals 0 because it's not accelerating up or down. And now I can start plugging things in and having some fun. Okay, so FR plus 2FR, because that's my leftward force, minus FM equals 0. So the force of gravity from the mass is equal to 3 times the rightward force. All right, now force of gravity of the mass, that would be 10 times G, which is 10 times 10, is equal to 3FR. That means that my force on the right-hand side is going to be equal to 100 divided by 3. And of course, leftward force is twice that, so that's 200 divided by 3. right, now, in all those cases, torque equals 0. If it's not, okay, well, in the example problem it didn't, but in those two examples I just did, torque equals 0. Doesn't always have to equal 0. If it doesn't equal 0, then your FR sine theta equals I alpha, or moment of inertia, times your angular acceleration. And this beautiful equation right here becomes important. And I like this one. All right, here's one that's going to actually ask us for the angular acceleration. So when we look at this equation, we're going to say, all right, we're looking for the angular acceleration, and they gave us a bunch of masses, so they gave us forces. Now, no angles, so we're good without that. So I alpha equals FR sine theta. Or in this case, just FR because there's no angle. Or sum of my FRs. Okay, so let's start with this. Moment of inertia. Did they give it to us? Sadly, no. So that means that we get to do sum of mr squared times alpha is equal to the sum of the forces times their r. All right, so my masses, let's do moment of inertia. I've got 3m naught, which is a distance L, plus m naught, which is a distance 2L. Make sure you remember the square. So all that times alpha is equal to the sum of the forces. Okay, so my pivot point is here. I've got a force acting from each of the masses. All right, counterclockwise is the 3m, so that's 3m naught L minus m naught 2L. And then we simplify. All right, so on the left-hand side, I've got 7 mass L squared. It's 7 because remember that 2 is squared, times alpha equals 1 m naught L. Okay, cancel out what can. Got an m naught on both sides, got an L on both sides. You end up with 7 L alpha equals 1. Divide by 7L. Alpha is equal to 1 over 7L. Nothing too bad. All right, let's move on. All right, this one might look tricky, but he's not. Okay, so I've got this like a yo-yo hanging there, and I need to pull up my hand at a certain speed, and I'm doing that, in which the yo-yo will not move. Okay, so I have this nice, beautiful equation here. Now they want the linear acceleration, so they want me to be using acceleration, so they want alpha, because that's acceleration angular, but we can get that into linear. And they gave us forces, like tension, so they want us to use this. So we're not even going to worry about that part. Okay, so I is right here. So I have 1/2 mr squared. All right, now alpha, you can leave it in terms of alpha and put it linearly later. I'm just going to do it now so I don't have to worry about it later. Okay, angular acceleration is linear divided by radius. Now sum of the forces times the radius. Well, the force acting on it is T, that's the tension, and its distance is capital R. Okay, so let's simplify down. One of my R's can go away. Right? Oh, that should be a capital R too. So then the other R can go away. And we end up with 1/2 MA equals T. Okay. Now the problem is we're not quite there yet. Because if this was a multiple choice question, they didn't have T in the answer. So this is when we're like, all right, we've done all we can with torque. Let's go look at the sum of our forces. So if I'm going to look at the sum of forces on the system, and part of the reason why you know that is because they tell you the center of mass does not move, which means you know the sum of your forces is 0. Okay, which means that your tension acting up is equal to the force of gravity on the center of mass. Okay, those two aren't equal. which means that your tension is equal to mg. Okay? So 1/2 ma is equal to mg. Mass cancels. Acceleration is equal to 2g. So the acceleration of my hand is 2g. All right, that's the end of the lesson. Good luck.